Discussing bipolar transistors. Now, transistors are used in amplifiers. Transistors are also used in switching circuits. Now look, what I want to show you here is really a toy. This was a gun that was really used in a laser challenge type of game. Now, let me get a bit closer and really show you this. Okay. What I want to show you here, let's get a view of this, all right? There's this little board over here. This is part of the circuitry for that gun. Now, if we look at this quite closely, what we have here is little black things here with, if you like, you can see it, we have really 3 legs associated with each one of these little black things. These are the actual bipolar transistors. So these are bipolar transistors. You can also see some resistors on the board as well. Okay, and then on the top of the board, just to show you here, we also, not on the board, on the gun, we have some LEDs. Okay, these used to actually sequence through as you shoot the gun. Okay, the bipolar transistor. Bipolar transistor. All right, let's look at the symbols, okay? So we'll draw these symbols like this, like this, like this, and here. Okay, I'm going to show an arrow indicated like so. This would be called the collector, this is called the emitter, and this is called the base. Collector current flowing in this direction, we'll call that IC. Emitter current flowing in this direction, we'll call that IE. And base current flowing in this direction, we will call that IB. Okay? This is a symbol for an NPN transistor. All right, let's show the PNP transistor. All right? Down like so, like so. It's our symbol. All right, this time this little arrow is pointing in on that emitter lead. All right, this is the collector, this is the emitter, and this is the base. Okay, let's show you the current directions. This is the emitter current, IE. This is the collector current, which is IC. And then this is the base current, which is IB. This is a PNP transistor. Our focus is really going to be on the NPN transistor. If you understand the material for the NPN transistor, you will understand the material for the PNP. It's just that the polarities will be the reverse. Okay. Let's talk for a moment about normal operation. Okay, so for normal operation, the emitter base junction is forward biased. The base collector junction is reverse biased. Let's look at a NPN example here. All right, so look, I'm going to show you sort of the semiconductor configuration. All right, what we have is really N-type material, P-type material, N-type material, NPN, okay? This is the emitter, this is the base, this is the collector. This is a pictorial way of looking at it. Okay, the emitter base junction should be forward biased. So let's show that. There we are, with the positive side connected to the base. The base collector junction is reverse biased. This is for normal operation. So we'll show that like so. This is the positive side connected like this. Okay. Now let me give you what I feel here is a current summary. Now these are the currents that you really need to know and understand. Okay. Now we are making some approximations in all of this, but we're focusing really on what I'm considering here to be essential. Okay. So again, a focus on an NPN transistor. I'm talking really here about a current summary. All right, let's show you the transistor once again. Symbol. All right, here it is. Looking like this. It's an NPN transistor, little arrow pointing out. Okay, like so. Okay, this is the collector current, IC. Of course, this is the collector, this is the emitter. So this is the emitter current, IE. And then this is the base here. This is the base current, IB. All right. Important equation. The emitter current, IE, is equal to the collector current plus the base current, IB. Now that may be obvious from that drawing. Base current coming in, collector current coming in, emitter current coming out. Emitter current is equal to IC plus IB. Okay, there are two other relationships I want to show you in these equations. One in particular we'll be using a lot. This is this one here. The collector current, IC, is equal to beta times IB, the base current. Now, typical values for this beta, all right, if I look at typical values here, well, we might be seeing betas of 50, betas of 100, betas of 200. A lot of what you do in the lab, for example, you're going to have transistors that have betas somewhere between 100 and 200. And a lot of examples, just for convenience, we will use really a beta of 100. Okay. Now, what does that mean? Look, it means that really, if I choose, for example, a beta of 100, it means that the collector current is 100 times bigger than the base current. 100 times bigger than the base current. So the current here is very small compared to the collector current. Okay. One other equation that we'll show you, okay, and that is this. The collector current is really equal to alpha times the emitter current. Now this alpha term here, based really upon a large beta, this alpha is very close to 1. So it might be a value, for example, of 0.99. In other words, it's close to 1. Okay, so that means that the collector current is really approximately equal to the emitter current. And isn't that true? If I look at that first equation, okay, remember, really from this, I'm saying to you that the base current is very small compared to this collector current. So if this guy is very small compared to this, then this is approximately equal to this. Okay, now what you could do here, as you look at the text, you could actually maybe derive perhaps a relationship maybe between, let's say, alpha and beta. So have a look at the text in relation to that and maybe use these equations here in order really to derive that relationship. Okay, I think at this point really you should take a break and you should read this material up to this point really in the textbook. Make sure you're comfortable with what we have just discussed.